So in case if you are expecting to have some symmetry restored in your theory, etc., then it's not the place. I am actually going to talk about something specific, Hadron spectroscopy using lattice QCD calculations or from lattice QCD calculations. And I am not planning it to be I'm not planning it to be a fundamental perspective or some very detailed perspective. I'm just going to glimpse over and give you a glancing view over whatever is practiced, and I hope you will get a flavor of how these things are actually done. I will definitely not touch upon a very bit of details. I will just simply go through certain parts, and I will simply skip certain parts, and I will give you some references where you can actually find details of such calculations. So spectroscopy is actually very interesting in the sense that actually this is something very basic, something that you can always start with when you actually try to study some theory. So an example or a clear perspective you can get it if you just look through the, I'm not an expert in pedagogy as well, but if you just look through the development of quantum electrodynamics, you can actually see that starting from actually, so initially we did not have a picture of how an atom is composed of. People actually proposed, like Thomson proposed this some plum pudding model kind of stuff. Then Rutherford's experiment clearly said that actually there is a positively charged core nucleus and some electrons revolving around it. Then Bohr said that there should be some orbits, and Schrödinger corrected that there will be orbitals. And later on, there was also this observation of Lamb shift, which actually said that, of course, we need some quantum electrodynamics theory to explain this existence of Lamb shift. So if we could understand the spectrum, then we can say more about the theory itself. So it's the same perspective, same reason why we are also interested in understanding what is going on in Hadron spectrum. Now you have been actually hearing about protons, pions, and possibly some kaons, and also some quarkoniums possibly in most of the talks. But in principle, if you look through the particle data group, you can actually see that there are several, more than 50 states that are observed, which are actually marked with 4 stars, which are very well established, which are considered as hadrons. There are many more states which are established with 3 stars and 2 stars and 1 star, etc. The star is basically giving a credential of how reliable this state is or how established this state is based on experimental evidences. All right. So some examples that I can give are, I'm sure you may not, you have never heard of this state N1440. This is basically radial excitation of nucleon itself. You can see it here. Yeah, okay. So we still don't really have a clear understanding whether it is really composed of a 3 quark state or a 4 quark and an anti-quark state. It was actually introduced, this kind of state was introduced by Roper and back in 1964 or so, where when he actually investigated the finite state spectrum of n pi, and he found that there is some phase shift increase, and he has to actually include a state like this to interpret why this phase shift is rising. Okay. So this way actually he argued that there will be states like this. So N1440 is not just one state, there are many other similar states that needs explanation, and many of these states basically are very short lived. Multiple reasons why it is actually difficult to detect these kind of states and in the final state scenario. That's because they are very short-lived. They can only be identified based on the final state distribution. So if you can actually find out certain kind of final state configuration are actually peaked up, then you can actually point out that, okay, there is possibly a metastable state that might be giving rise to these kind of peaks in the final state cross-section. So N1440 is one such example. This is actually a very aged example. Now these days actually there are almost every month there are newer and newer states that are being observed in experiments, and we still don't have complete understanding of whether we can interpret everything based on simply QCD. Okay, it's partly because you already saw this figure on strength of strong interactions as a function of scale in Swen's talk, where it was actually said that actually at low energy scales where your hadrons exist, this is actually a highly non-perturbative theory. And unlike in quantum electrodynamics, where you can actually apply all this perturbation theory, you cannot actually apply perturbation theory to understand hadron physics in that regime. So you have to go for some non-perturbative procedure, and this is exactly what lattice QCD procedures provide. Okay. All right. So what I will actually do, the plan of my talk is actually, like I said, it's just a glancing view over how lattice QCD calculations are done. I will actually not go into any of the results, etc. If I am going to the results, then I will also have to talk quite a lot about infinite volume physics. But what I will actually try to say is how lattice QCD calculations are done, or to be more precise, if I want to put it in one sentence, I would say that actually how excitations or highly excited energies are extracted on the lattice. Now, the thing is, when I say this statement, you might be wondering why should I even care about why you are actually extracting excited states. It's exactly what I am going to talk about in this lecture, and I hope I will convince you that it is very difficult to extract excited state, and unless you have information about these excited states, you cannot access any of these higher lying states. For example, this N1440, like I said, this was observed in the final state of N and pi. Now, unless you can extract all the excitations in this energy regime 1440 MeV, so this is the energy of this is approximately 1440, that's why it is named as. So this is around 500 MeV higher than proton. So unless you have access to all the energy final states, you cannot actually say anything about what is going on in this energy, whether you can really say something like there is indeed a state at this energy, this is predicted or post-predicted by lattice QCD calculation. So you need to actually access those energies. And unlike in the experiments, of course, experiments have their own complications, they have their own difficulties, etc. Just like that, even on the lattice, we have our own difficulties. One of the clear difficulties on the lattice is that unlike in experiments, you cannot simply tune your center of mass energy. So what we have to do is we have to go step by step. So we have to actually understand every bit of details until this energy, and then only we can say something about it. Okay, so I'm going to actually make this clear a bit more throughout my talk. So to start with, you already heard about path integral, etc. So I will start with this expression. This is in the Minkowski space. I don't need very specific details about the theory, etc. What I am actually trying to give you a brief idea of how Monte Carlo calculation is done, so that you get a feel of what does it mean by ensemble average, etc. when I talk about it later on. Okay, so that's why I'm just saying about it. Now, if your theory is actually, if you cannot solve your theory exactly, you basically try to investigate correlation lengths that exist in this theory. So basically, you go ahead extracting correlation lengths, various correlation lengths in that theory, and this is how you study about what is going on in the theory. Now on the lattice, what we do is, you already heard Professor Haidar's talk. We do a weak rotation. What will happen is actually your this part of the Lagrangian will basically look like, so this is in the Minkowski space, and if you go to Euclidean space, you basically have, I put a tilde to indicate that this is on the Euclidean space. Now the thing is, you can actually see that this becomes a positive definite weight, so that you can actually consider this as a probability density, and you can utilize this to do something called Monte Carlo simulations. Okay, this is all what I want to actually say about Monte Carlo simulations. So now this is actually a positive definite weight. Okay, so then what you can actually do is actually Monte Carlo sampling. Now there are two kinds of Monte Carlo sampling. I actually give you some, I just want to give you an idea how this really works. So that's why I just say it actually in a standard fashion, also in an important sample fashion. So you can actually evaluate these kind of correlation functions in this format as well. What you basically do is, all right, so you can see that this is basically like a statistical mechanics partition function. This was already discussed in Professor Haidar's talk, so I am basically skipping various details. but you can see that actually if you, what you can do is, this is basically like an evaluation of an integral. Okay, so let's actually consider an integral like this. For example, let's consider that there is a function like this and you want to evaluate the area here. What you can do is you can actually just throw stones. Okay, throw stones in a way that actually you actually throw stones in the sense that when you throw stone, it's actually kind of picking a random number. So you consider an interval a and b where you want to do the integral, and you know that this is your f max of x. Okay, now what you do is you throw stones in this region, find out how many stones have actually fallen inside the shaded region, and that basically gives you the area of the function in this interval. Okay, so you can actually randomly throw stones inside this, and if you throw n stones, and if n is the number of stones that falls inside here, then basically n by capital N times the total area, sorry, b minus a gives you the area under the curve. Okay, you can also do this in a, so this is actually naively called as a naive or standard Monte Carlo. So you basically do throw stones in the into this region, and you actually find out what is the ratio of stones that fall underneath the function, and based on that you can evaluate the function itself. Okay, instead of this, what you can actually do is you can actually throw stones in an important sample way. How do you do that? You of course continue doing sampling along this axis in a random fashion, in a uniform fashion, but along this axis, but for the second random number that you generate along this direction, you actually put a random weight. So the second random number that you generate for a value of x here will have larger weight than a random number, second random number that you generate at this point. Okay, so this way you see that actually the random numbers, the pair of random numbers that you generate to evaluate this integral will always fall around this region. Okay, and in the second category, which I call as important sample Monte Carlo, sorry. Okay, so what I basically did is I sampled the configurations, or so sampled the random numbers, in fact with a probability equal to this e raised to minus s phi, and this way whatever I get as the distribution is simply giving me the integral value. All right, so this is called as important sampling Monte Carlo. There are many more intricate details that one can actually talk about it. All what I want is actually to say that we do something called an important sample Monte Carlo, and if you actually get a feel of it, then you can actually just go forward. It's actually not really necessary to know about the details to understand Hadron spectroscopy, but as long as you get an idea that you can evaluate the correlation functions this way, you can go ahead doing Hadron spectroscopy. All right. Now you actually define your theory on the lattice. So this you already have heard it from Professor Hadra's talk. So for lattice QCD you need gauge fields as well as fermion fields. So you put your fermion fields on the lattice sides. Okay. And you put your gauge fields as links. All right. So this way of latticizing, you get an ultraviolet cutoff, which is actually given by the lattice spacing that is put here, and you get an infrared cutoff that actually is coming from the finite volume that you are introducing here, and your fields are actually defined in this format. And what you basically do is you construct gauge invariant observables to construct your Lagrangian, construct your observables that you are going to measure, and you basically measure this gauge invariant observables on the lattice, and you follow important sampling to evaluate such correlation functions on the lattice. All right. Yeah. So this is the lattice spacing. This is basically equivalent to a cutoff that, infrared cutoff, right? Yeah, sorry. So this is the finite volume of the thing that you put in. You cannot actually do any calculation in an infinite volume. If you have infinite volume, then that means there are infinite number of points, and you are actually doing some computation calculations. You cannot fit that into your computer, right? So you have to actually put in a finite volume, and that actually gives you some infrared cutoff. Finiteness of the volume gives you infrared cutoff.
Okay.
Okay. It's a matter. Sorry. All right. So this much said. I don't want to go into details about gauge action, etc. This you have already heard about it. I will just briefly say a few things about fermion part of it, because this might be useful when I talk about correlation functions, etc. So you have your Ganjan. Alpha just refers to the species of the fermion, and mu are the Dirac indices, and this, in short, I write it this format. Why I want to actually talk about it is because there are certain factors that come in, and these are the factors that are important while calculating Hadron correlation functions. All right, so first let's write down the partition function. Maybe one thing that I would like to, a couple of things I would like to repeat about this importance sampling and Monte Carlo, standard Monte Carlo. In standard Monte Carlo, let's say, so like I said, we are actually just throwing stones in a big phase space. So you have some big phase space here, and what you are actually doing is you are actually throwing stones across the entire phase space, trying to figure out what is the ratio of means which are the means basically trying to evaluate the observables. But in importance sampling, what it does is actually it tries to find out the region in the phase space that is more important or that is contributing more into the partition function. So if you actually think in terms of the action itself, you can actually see it this way. So these are the microstates, and if you consider this as the action and assume a very nice scenario where you have a clear global minima, then what importance sampling does is actually try to actually go towards the minima and try to actually scan this region more and more. So the advantage of actually doing importance sampling is that actually even with limited number of such random numbers, you can get much better estimate for whatever you are trying to evaluate. So let's say if you actually go ahead with standard Monte Carlo, then you may have to actually go for some. So if typically phase spaces are very large, 10⁻⁸ or 10⁻XVI microstates, etc. You cannot scan throughout the entire phase space in your lifetime even. But with important Monte Carlo, you can just leave with 100 or even 1000 is already good enough for typical lattice UCD calculations. So this is one of the major advantage while using importance sampling Monte Carlo. Okay. So now I would like to write down the this is actually not important, but I am still writing the gauge field part. Okay. Now this, from your field theory exercises, we know that this is simply this we have already seen in Professor Harida's talk, that we get a determinant that basically encapsulate all the fermion dynamics that is coming from the action. It's actually a very highly non-local object, which means that if you are really going to evaluate the entire determinant, that is actually going to be very expensive. So in the past, actually what people used to do is to just drop this determinant, or in other words, you put this determinant to 1, which equivalently means that actually you are assuming that all of your quarks are actually not giving any dynamics, or in other words, you can assume that your quark is infinitely heavy to be popped out from the vacuum, so that you need very high energy, means infinitely large energy. So if you put this simply to 1, all the quark dynamics that is coming from the action is just put to 0. All right. So, but in the recent times, people have actually come up with newer and newer algorithms which can actually determine this, evaluate this determinant of M, and people actually do calculations including this determinant of M. But this is not the factor that I am primarily interested in. I am interested in the second quantity that I am going to write down in a moment.
This determinant was already there in the weak force.
Sorry?
It was already there.
Yeah, but it was not that common. Now it has
It was
become more
in
common.
thermodynamics. It was
Okay.
there was this.
But in spectroscopy, even in 2000s, people were just using, early 2000s, people were just using.
So that lived when those people had developed this RHMC, the HMC initially, and then RHMC came in 2006.
But to my understanding, for Hadron spectroscopy, it has become more common only after 2005. Yeah. All right. Now, what I am actually interested in is this second thing that we are going to observe. So, like I said, we are interested in evaluating correlation functions or correlation lengths that exist in the theory. So, one of the correlation length that is interesting to me is this. Now, I am actually going to drop this gauge part because that's actually not immediately interesting to me, at least for the following discussion. This mxy inverse is what I am interested in. So this one says I should have a bar somewhere here and an x and y, right? Oh, I wrote it correctly. Yeah. So this mxy inverse is basically presenting the propagation of quark from y to x. Okay, so this is equivalently a quark propagation line, or in other words, you can actually say this is a quark line, and this is what I am actually interested in. Where? Yeah. Yes. So you can actually go ahead evaluating similar objects. Why? So this one you can actually already see that this one looks like a meson. You have a antiquark and a quark. So this is the kind of correlation function that I will be evaluating. But here it is just one meson point, but you can, if you want to really investigate meson propagation, for example, then you need to have a quark being created and an antiquark also being created. So in effect, what you will basically have is this psi bar. So now you can actually see that there are two quark creations, two quark annihilations, which means that you can actually contract in two different ways. One way you can actually contract this way, and these two different contractions are actually differing by just one quark interchange or fermion interchange that will introduce a negative sign. So I can write this down as, maybe I should just use the notations that I have used in my notes. Maybe, sorry. I'm also going to drop this determinant of M because that's actually, I assume that this is already inbuilt in the Monte Carlo simulations that I make initially. So later on, I'm actually going to drop this term as well as and when it is convenient. All right. So what you can actually see that we have, can I have the slides open? Very fast. Okay. So you can actually see that we have two different terms corresponding to two different kind of contractions. So here actually, doesn't it move? Yeah, sorry. So here you can see that, so I am probably missing, yeah, yes. Where is the pointer? So this is first kind of diagram that gives you, oh, sorry, no, not this one. Do I not have that diagram? Probably don't have it. That's fine. So this is equivalent to saying that if I have a lattice like this, if I call this as W, X, Y, and Z, the first diagram basically connects me like this, and the second diagram basically connects like this. Maybe I should use a different color chalk. And this crossing introduces a negative sign here. All right. So this is the way you calculate correlation functions for mesons in the theory. Now, yeah, okay. One more thing, there is a usage that I always use. That typically these dynamics that comes from these insertions that you put in here, the operator insertions here, these I generally refer to as valence quark dynamics, and whatever fermion dynamics that comes from determinant is typically referred to as C quark dynamics. Okay, so in case if I use that, just assume that C is basically whatever dynamics that comes from determinant of M, while this one carries all information about the valence quark dynamics. Okay, so this is not yet, whatever I have drawn here is not yet any meson correlation function. These are just some 2 quark and 2 anti-quark propagating from one point to the other. Now I will come to the meson part in a moment, because I have not actually constructed any color singlet object. Meson is actually a color singlet object, so I have to construct some color singlet object to actually represent a meson. All right. So this much is already some warm up for whatever I am going to discuss now. Any questions? All right. So now I can actually switch to the slides that might help. I will anyway write some more expressions here. So now I am actually interested in meson correlation function, and I take the simplest meson for all these arguments that I am going to make. I know that my gamma phi is like a pseudoscalar, and I can construct a pseudoscalar meson, which is actually the meson that we all are primarily interested in. Pion is what you actually see in experiments, right? Directly see in experiments. So gamma, this one represents basically a pion-like object. Now what I am going to do is to construct correlation functions for this kind of object. Right? So this is what I am interested in, and the fact that actually I have actually suppressed all the spatial index. So sort of what I assume is that these are all zero momentum projected mesons. So these are at rest, and which means that these are actually, there is a spatial sum here involved, and there is also a spatial sum at x prime equal to 0, or I should say at t prime equal to 0, I am actually doing a spatial sum. Okay, which means that this whole correlation function incorporate propagation of a meson from any spatial point in this particular time slice t to any spatial point in this particular time slice t prime equal to 0. Okay, so this is sort of a highly non-local object, but I will actually explain in a bit more detail later on. Now I can actually incorporate the time dependence of such an object by explicitly writing down the explicitly taking out the time dependence. This will give me psi and this you can write it down as or else simply write this down as so here I have actually inserted an identity, and then you can get an expectation for your correlation functions in a spectral decomposition form. So what you naively expect is that if you construct correlation function like this, then you expect that your correlation function will behave like this. This is just an expectation. I am not really saying that this is the way you compute the correlation function. This is just an expectation. Once you have the correlation functions, then you expect that they behave this way, and if that is indeed the case, remember this is actually on the Euclidean lattice, and that's why you don't have an I here. Now since it is on the Euclidean lattice, if you go to very large and large times, any higher lying states will die out, and whatever will be remaining is the ground state. So what you can do is you construct correlation function like this, look at the very large times and try to figure out what is the state that is encoded, what is the state that has information encoded in this correlation function. All right, so this is what we do. I need the slides now since it is very fast. So now you can see that such a correlation function has been plotted. It's actually not the correlation function. So you can see that correlation function has this kind of expectation, and if that is indeed the case, at very large times it is basically the E naught, the ground state, that should dominate. So what one can do is actually you can evaluate such an object like this, where this is actually log of ratio of correlation functions at neighboring time slice, and in this way we expect that this object will basically saturate to some energy which basically represents the ground state energy. And Hadron spectroscopy is mostly about trying to determine what is the ground state energy here. This one sounds like it is, so whatever we do, whatever I said now is relatively obvious, is pretty standard now. But what is more complicated is that if you want to know information about the excited state, then this becomes a problem. I will come to that in a moment, but basically what I am trying to say is that you just look at the last time plateauing, and from that you can extract the information about ground state energies. This is basically what I am trying to say. So at very large energies, you can just go for some single exponential fit forms. As I said, you can actually drop all the higher energy terms here in this summation and just use the leading term and try to get what is the ground state energy. Now, if you want excited state energy, of course, you can go for multiple exponential fit forms. You can actually include more and more fit forms. Yeah.
What are these uncertainties encapsulated?
Yeah, I'll come to that in a moment. Okay, I'll say that. So you can go ahead with multi-exponential fit and try to see what kind of energies you can extract it from early times, because actually they will die out at very early times, relatively early times. So any information about excited states are basically encoded at very early time slices. So you basically go on trying to get more information from earlier and earlier time slices, and you can try to extract. But there are twofold problems. One is actually the more number of parameters in your fit, it will become more and more unstable. Second thing is actually if you want 2 or more, then you basically don't have enough points to really fit. So you are basically, your fits will be basically under constraint. You have very less number of points. Now about the uncertainties that you have asked. So like I said, we are actually doing a Monte Carlo calculation. So it's, so what we basically do is we are basically sampling over the phase space in an important sample way. So you get some number of copies that represents the microstate in the phase space, and based on this kind of estimate, you can actually get what is the correlation function that exists in the theory. The same way, these are basically statistical procedures. You can estimate errors from the, and those are the errors here. There are error propagation methods. I don't want to discuss those things, but you basically can estimate. These are basically just statistics, statistical errors that you get from calculation. All right. So now you can actually go ahead evaluating the correlation function. How do you extract the correlation function? So I already said that you don't have to project it, you just keep these slides here. I already said how actually you can contract your quark line or estimate your quark lines. They changed it. So you basically follow the same procedure to extract the correlation functions for mesons. So what I have shown here is basically a meson starting from 0, 0. So one of these is actually spatial index, the other is time index, and ending at a point xt. So here you can actually see that I suppressed the x index and I said that this is basically momentum projected. I purposefully did it to actually emphasize some difficulty that we encounter in this whole calculation. So here I have explicitly written it out. So you can see that this is actually a meson starting from one point and ending at other points. So this is actually one set of quark line that you get, and you can see here that, so this should in principle be this taxi driver metric kind of propagation. I just drew it by hand, but in principle actually all this information is going through the links. Okay, so it's basically a taxi driver kind of metric. So the first diagram you can see here is actually okay, yeah, I have already written it here. So you can actually contract this object as well, same way what I have written here. So you get a set of contraction where there is a single trace, where the quark is actually propagating from 0, 0 to xt, and there is also a quark propagation in the reverse time direction that goes from 0, 0 to xt in the reverse time direction. All right, and there is another term because of switching off the contraction that will actually give me two traces. Actually, I am surprised why there are no two traces. This is actually a mistake here. This is actually mistaken here. So you can actually follow this thing. So you can see here there is a single trace that represents this diagram, while the second diagram has this is also wrong. I should have two traces here because there is color tracing at each point. Okay, so this actually, you should see this as this way. Now I have to take the chalk. Sorry, I wrote it very wrong, very fast. So the first term is basically trace of and the second term will have a trace of right. So what that just means here is that here there is a quark propagation that starts from 0 going to x, while there is a quark propagation in the reverse time direction, and these ones are basically a self-annihilating. So it's basically a quark starting from the same point and ending at the same point. All right. This part of the calculation is very difficult because this is typically referred to as disconnected diagrams, and this is very difficult to evaluate for the following reason. We already have some difficult part in this calculation, in the sense that I have actually suppressed the spatial index here, and I said that here this one encodes information about meson propagating from every space point in time slice x to every space point in time slice 0, while here I have actually explicitly written out the x to actually show what kind of quark lines are involved here. So if you really want to evaluate propagation from all space points to all space point, a typical lattice size is around 20 along one direction, one of the spatial direction. So 20 into 3 dimension is basically some 10 power 3, 10 power 4. While you have also source and sink, which means you have around 10 raised to 8 different kind of contractions, quark lines to evaluate. And typically each inversion involves, like if you consider a typical lattice, it involves like 3 minutes or 4 minutes of evaluation, which means you have to actually spend around 10 raised to 8, 3 or 4 minute inversions, which means you cannot do these kind of things in a lifetime. So what I simply want to say is that if you want to really construct a momentum projected meson on the lattice, this is possibly becoming a impossible task. All right. And the same is also case here. So here what I have here is basically a trace over color or of product of gamma phi times the quark that is starting from X to the sync point, starting from the sync point and ending also at the sync point. Now if I want to actually evaluate this at every sync point, then that means this is going to be an impossible task. You have to evaluate it at every spatial point and every time point. Maybe I should have mentioned one more thing here. So typically this M inverse, this is basically some linear algebra. Okay, so when you typically think about a matrix inverse, you have some 3 by 3 matrix. You simply think about another 3 by 3 matrix representing it inverse. But here we have actually a lattice that is of 10 raised to 6 or 10 raised to 7 points, which means if you have a matrix of 10 raised to 10, 10 raised to 14 kind of elements. So if you want to really think about inverse of a matrix in such large dimensions, then it's really impossible even to put that entirely on a computer, because you can just evaluate the amount of bytes that you may want to actually you may consume if you actually save the entire pop-up data. So instead of that, what we generally do is the following. All right, so I can actually erase something from there. So you know that this is just you can actually evaluate inverse. Inverse is basically a linear algebra problem. So you have some m x equals y, and x is basically your m inverse of y. All right. So y is actually a column vector, x is another column vector. This is actually a matrix. So instead of evaluating the entire inverse across the entire space, what you can just do is just invert it for a given column vector. And typically that is what all you want. So yeah, actually it's better to, can I have the slides back? So y is basically a source vector that you put in at one point, and whatever you get, this is actually a free point. So you can see here that there is a set of space-time index that is coming here. There is another set of space-time index that is coming here. So if you call this as the source, the space-time index at the source is gone after this inversion, while you still have handle on space-time index at the sink. So if you call this as the source, then you will lose any control on the space-time index at the source, while you still have some control on the space-time index at the sink. So you can actually play with the sink point, try to actually project various things, but at the source you have to actually carefully define what you have to do. Okay. So what typically people do is people decide a source function that actually effectively projects to what you want, or what kind of modes that you want to excite. All right, I will come to that in my next lecture a bit more in detail, but main thing that I want to emphasize here is that you don't really evaluate mx inverse for any fermion matrix as a whole, because that itself can carry like several TBs of data just for one configuration. So you simply cannot save it. What you instead do is actually you just invert your co-operator on certain column vectors and just save only those resulting column vectors as what you will use in your correlation functions. So this is again just some column vectors that you use here. In this sense, this is simply some that you put. All right. I would like to see the next slide as well. So it's not just for mesons, baryons also go in the same way. So you can actually build baryon operators like this. On the top you can actually see I have built a baryon operator for lambda baryon. Lambda baryon is a baryon that is composed of a U quark, D quark and an S quark, as you can see on the top. And basically the Bij K stands for all the structures inside, whether it is gamma structure or spatial structure or anything, whatever is inside. And UDS are the flavor things, and you basically contract. There is only one single contraction that is possible in this particular case, but if you consider nucleon, you can have two different contractions. If you consider delta baryon, where you have UUU kind of flavor structure, you can have in total 6 different kind of contractions. So here there is only one contraction, and I just wanted to show the simplest possible case, and you can basically construct correlation functions in this format. And U inverse is basically the M inverse corresponding for the U quark, D inverse is M inverse corresponding to the D quark, and S inverse is corresponding to the S quark. Now something that is interesting that you can notice here is that baryons have only quarks, right? So you have only forward propagation of quarks. So it is actually easy to deal with baryons. If you just consider quark propagation, if you just consider baryons as a 3 quark object, it's relatively easy to evaluate this thing. Because all of them are forward propagation. While here actually you have some backward propagation you have to deal with. I did not actually say how we deal with backward propagation, I will say that in a moment. But I already mentioned that there are certain technical difficulties in the sense that you cannot actually evaluate the entire M matrix. You have to leave with certain parts of it and just extract your correlation functions from those certain parts. Now something more about this reverse propagation here. Does not really discuss in detail. I also don't really plan to discuss in detail. I will just invoke that symmetry here and just try to explain that how that can be utilized to evaluate the correlation function. There is this symmetry called gamma phi hermeticity, which means that actually your action, fermion action, has this symmetry. Typically all lattice actions have this symmetry. This sort of relevant in the sense that if you want to have a positive definite determinant of M, you need to have this symmetry. So if you actually assume this thing, that's already enough. So you have this symmetry for most of the lattice action that you deal with, unless you put in some chemical potential or some, I don't know, some theta term or something. So most of the actions have these things. So we take those actions that has this kind of symmetry, and we can actually utilize that to evaluate the reverse propagation. This symmetry also carries in the inverse of the matrix as well. So I should actually have written this as, there should be a phi here, because I already used M for the fermion matrix. Okay. So this also carries for the inverse as well, which means that you can actually write down M dagger inverse as where dagger is on all the index that involves in the fermion matrix. If that is the case, then you can actually write down. So here there is a propagation that goes from 0 to x, while what we are concerned is actually a reverse propagation. If you want reverse propagation, like I said, we are typically inverting propagators only on one point. So basically you lose all control over the source index, while you have control over the sink index. But if you reverse the direction, then your source sink becomes source, but you are not really inverting over the sink, you are only inverting over the source. And if that is the case, and if you don't have this symmetry, then you will have to go ahead inverting at every sink point, which means it will automatically increase the amount of computation that you need. But this symmetry comes in help, and what you can do is you can actually then write down your M0x here as I missed a dagger here. No, dagger is already taken care by the 0x. All right. Now, if this is the case, then star. You can actually put a star. Okay. Then you can utilize this symmetry and replace this object like this. So I am just now talking about this object. This I anyway don't have any way to evaluate it at the moment, so let's ignore this part. So if that is the case, then I can write this as, no, I can just get rid of the gamma phi here and write this as star inverse, actually inverse is, yeah, 0 x 0, right? Just a minute. This is simply my pion correlation function. Okay, I can ignore this part for pion for the following reason. So pion is basically this object, typically indicated with this. This has either u bar d these are the three different pions representing pi plus, pi minus and pi 0, pi minus, pi 0 and pi plus. Now if you actually consider such correlation function, you can actually take this as an exercise and you will notice that if you make the contractions in a correct way, this term simply drops out. Such self-annihilating diagram simply drops out, which simply means that if you are just interested in only in pions, you don't really have to care about these terms. But pions are not the only mesons that we know of. We have many other mesons to actually deal with. Here I am just giving you a feel of how calculations are done. But when you really start addressing certain Hadron correlations, then you will have to deal with certain other kind of mesons as well, which involve these kind of diagrams. And one such case is actually a sigma meson. There is still controversy, sort of settled, but still there are people who believe that sigma meson is really not a meson. We don't really know about the pole position of sigma meson, but let's assume that sigma is still a meson. So this is actually isospin 1 and spin parity is 0 minus plus, all right. This one is basically u bar u plus d bar d, isospin is 0 and jpc is 0 plus plus. Okay. Sorry? Sorry? Yeah, I actually just highlighted only the flavor part. I just indicated on, you are referring here, right? So here there should be a gamma phi. I only highlighted the flavor part of it. Okay. So this minus sign actually brings in the difference. Minus sign and the plus sign brings in the difference. This minus sign actually cancels out the two different double trace terms. While in the sigma meson, because this is a plus sign, this double trace term survives, which means that you will have to evaluate such self-annihilating diagrams and you cannot actually just get away with it. If you just drop it assuming that, okay, we are doing a first calculation, let's do something approximate for sigma meson, that in principle changes the entire physics. So you cannot simply avoid those kind of diagrams. All right. I have 20 moments, right? Okay. Now I am actually going to talk about excitations. So I already said a little bit about extracting excited states. So you basically look at the last time behavior of the correlation function, try to see how, try to see their exponential behavior in the asymptotic times, and from that you can extract the ground state. And if you want to extract higher lying states, then you go earlier and earlier time slices. But this has this problem that actually if you go for multi-parameter fit, then it becomes much unstable. You also have very less number of degrees of freedom, so you basically cannot extract the excited states in a reliable way. So you have to actually find out some other alternative, right? So and that's what I am actually going to talk about. So here I said about correlation functions. So what I do is typically when I construct correlation functions, what I do is actually I construct operators that has the right symmetries. Sorry. I construct operators that has the right symmetries of the state that I am interested in, because unless they have the right symmetries or unless they have the right quantum numbers, not the symmetries are the same for the entire Lagrangian, but I design the operators such that they have certain quantum numbers, and then that operators can in principle couple with that state. Okay, how do you identify the coupling with that state? So you can see it here. So when I actually extract out the time dependence, whatever is left here, and when I insert an identity here, I get some object here, right? I renamed it as Zn. This one doesn't carry any time dependence. In principle, it should not carry any time dependence. And this object gives me information about the quantum numbers of that state. So if I actually design my operators in a way that it has the right quantum numbers, then I can really probe that particular quantum numbers. Which means that I could also study the same pion with a different kind of operator as well. Only thing is, what will happen is my Zn will change because it depends on how well my operator couples with the state. Which also means that instead of one arbitrary operator, I can use some 10 different operators and try to study them together so that I can get a better estimate for the state, right? So what I can actually do is I can construct multiple different operators for pion, for example, and then what I can do is those I showed you this effective mass plots, which actually goes like this. I use more and more operators so that I can get better signal at even earlier times, so that I don't really have to care about I am actually slowly deviating, but you will actually get a feel of where I am getting at. Okay, so I can actually tune my set of operators such that I can get better estimate or larger region where I can safely estimate the ground state energy. Okay, which means that what I am trying to get at is, instead of single correlation function, you can evaluate correlation matrices. You can evaluate correlation matrices. So I just name it this way, where I and j refers to the operator that I use. Now this, I can write this down as, in the same way, I can write this down as, that I should be star. Yeah, correct. Just skip that 2en. Did I write the 2en? So you can actually absorb this 2en because that's also time independent. So you can either absorb it inside the set or write it whatever way you want, as long as your time dependency is clearly taken out. Yeah. So this way you can get a correlation matrix. Now you see, actually you can, for simplicity, you can consider a 2 by 2 correlation matrix. So you can actually write down such spectral decomposition for every element of the correlation matrix, right? So there is an spectral decomposition form for every element in the correlation matrix, and each operator can couple to the respective states given that they have right quantum numbers, right? What you can actually do is you can actually try to diagonalize this correlation matrix. So what will happen is the information about different states get distributed into the eigenvalues separately. It's sort of filtering out. Or in other words, what you try to do when you do a diagonalization is that you initially had a correlation function. Now once you have a correlation matrix, you try to present the evolution of a state as a linear combination of time dependence coming from different operators, right? So this is basically, this becomes basically solving an eigenvalue problem for extracting information about excited states, right? Now let me iterate this part once again. So this, here I actually construct correlation matrix. So what I do is I start with a basis of operators. and I use the Hermitian conjugated basis at the source and the original basis at the sink, which means that my correlation matrix is by construction Hermitian, right? So, use a basis of operators that has the right quantum numbers, and then use the Hermitian conjugated operator basis at the source and the original basis at the sink. Then I get a Hermitian correlation function. Now that my correlation function is Hermitian, I can diagonalize it. I know that Hermitian correlation functions can be, Hermitian matrices can be diagonalized. Once I diagonalized, I know that the states are independent of each other. So, information about each states or information about evolution of each state goes into the separate eigenvalues. And this is basically the idea of generalized eigenvalue. This is basically the idea of variation analysis in Hadron spectroscopy. Okay. So, what we basically do is we try to solve for this is typically referred to as generalized eigenvalue problem or generalized eigenvalue equation. It's actually simply an eigenvalue equation. Given that you have a Hermitian matrix, given that you construct your correlation matrix as Hermitian, you can do some Cholesky decomposition and rephrase this entire thing as standard eigenvalue problem. You don't really have to even go for a generalized eigenvalue problem. The only reason why we use GVP is because empirically it is seen that actually it is giving us better results for the following reason.
Is it T naught or?
Yeah, sorry. Yeah. Yes. So, this one, like I said, you can actually recast this as standard eigenvalue problem, because you have a Hermitian matrix, you can do a Cholesky decomposition, extract out the L dagger to the other side, and basically recast this entirely as a standard eigenvalue problem. The reason is that in this kind of format, your C of T0 is forced to be, in the diagonalized form, the eigenvalues at T0 is forced to be at 1. So that in numerical calculations, typically you get the noise that comes from the source to be suppressed. Okay, that's the only reason we go for GVP, but you can also cast it as an eigenvalue problem and solve for this thing. Once you solve for this eigenvalue problem, you get eigenvalues. You get eigenvalues, and at very large times they are expected to behave in this form. This you can actually see why this kind of behavior should be observed, because anyway each of the elements here had an expected behavior like this, and what you are simply doing is just some unitary transformation, doing some simple unitary transformation, so that you basically filter out the components from different states into different eigenvalues. The thing is, if you look at this kind of figure, each state actually are independent of each other, and if you are really looking at very large times, where you know that all of the eigenvalues have saturated, then you can expect that if you used an n operator basis to evaluate your correlation function, then at very large time you expect that the correlation function at those time slices will be saturated by the lowest n states. I can repeat this because this sometimes is a bit tricky. So if you actually try to extract the information about states, low lying spectrum, also considering very early time slice, this is a bit tricky because at this point the correlation function may not have been saturated with just those states. The excited state, some much higher excited state may also have information. So I can actually put it this way. So you actually consider a spectrum of states, all right, and let's assume that you used only 3 operator basis. If you try to extract the information about spectrum, even also considering earlier time slices, information from this also peeps in. But if you actually consider time slices where your signals have saturated, then individual eigenvalues, there will be 3 eigenvalues because you have a 3 cross 3 operator, and the time dependence of each of these eigenvalues basically will carry information from this and this states. The others would have died out, right? So this way you can actually evaluate the lowest excited states reliably. The more number of operators you use, the higher you can go. But if you have a statistics of 100 configurations, and if you go for 200 operators, then you basically already are losing degrees of freedom. So you typically go with some 10 number of operators, etc. All right. So this is the way one extract excited states from the lattice. I already said about considering different operators. I will give some examples of different kind of operators, and I will brief a bit more about how one can construct operators. I have 7 more minutes, so I can just utilize that for this. All right. What can I erase? So this I can erase. So you already saw a pion operator or a pseudoscalar operator. You can similarly construct a vector operator. Similarly for scalar you can construct this. I assume you already know it from your standard field theory exercises. Now this is not the only set of quantum numbers that you can live with. What I have actually just represented are just operators, quark bilinears, placed at one single space-time point. You can actually construct operators with these quantum numbers. You can already see that, for example, such an operator cannot be constructed with this local quark bilinear, which means that this is basically the main disadvantage with standard quark model. You cannot construct such operators. You can also see that there is no such operator like this. So you need some gauge field excitations to actually excite these kind of quantum numbers. So this is the idea of getting exotic quantum numbers, etc., although I am not going to discuss much about it. Now with local operators you are limited to just this set of operators, but we know that there are states that has quantum numbers spin 2, spin 3, etc. There is also a spin 3 state that is observed in harmonium. So how can you actually go constructing such operators? For that actually you can consider some displacements. You can actually pull apart the quark and anti-quark in a gauge covariant way and place such an operator which has some displacement or some derivative structure. A simple derivative, you can actually see this as a vector. This is basically a vector, right? And if you represent this in a circular basis, which basically means you actually represent your this basis, then this basically behaves or transforms like a 1 minus minus quantum number, which means that you can actually use psi bar di psi also for 1 minus minus. So if you are actually trying to study vector quantum numbers, you can utilize this operator together with this thing to extract your vector state better, or also access the excited states. It's not just one derivative, you can also go ahead with higher derivatives, or in a more general format what you can write is the following. So if you are interested in JPC, is there an I? I am not sure. These are basically Clebsch-Gordan coefficient M1, M2, M3, capital M. I can just use psi bar here of X, some gamma structure. I don't care what is the gamma structure here, M1 here, and a D, M2, D, M3, psi bar of X. So you can use two derivative operators clubbed together with different gamma structures to get higher spins. You can go ahead with higher and higher derivative structures and basically construct higher spin operators. Okay. So this one I just said it in an infinite volume continuum. Now you want to actually construct operators in the finite volume, right? The main difference between finite volume and infinite volume is the following. So your symmetries change. You originally had an O3 symmetry in your 3-dimensional space, which means that you have an O3 symmetry, so there is an infinite set of symmetry operations that you can do. So out of your entire energy states, if you do these operations, you will get to see that there are certain set of states that just rotates among themselves, and these are basically irreducible representations represented by your quantum numbers JPC. That's that JPC mentioned here. So these are your spin, parity and charge conjugation quantum numbers. Now on your finite lattice, what you have is just O3 symmetry. Sorry, on your finite lattice you have a octahedral symmetry. Typically we consider only hypercubic lattice, cubic lattices. We don't really consider any exotic lattice, because once you consider exotic lattice, this becomes more complicated. So most of the lattice calculations in Hadron spectroscopy is done with cubic lattices. So the spatial part of it has octahedral symmetry, and you have limited number of symmetry operations. You have just 24 symmetry operations if you exclude parity and double cover. Let's forget about double cover and parity for the time being. 24 symmetry operations. You have finite number of symmetry operations, which means you will only have finite number of irreps as well, right? Which means that in the infinite volume, you had infinite number of irreducible representation, and since this is just a subgroup of O3, the states should not change. States that existed in infinite volume should not change when you go to lower symmetry system. So what will happen is the states get redistributed into the irreps of this lower symmetry, right? What one can do is actually try to do the group theory for the higher symmetry as well as the lower symmetry, try to find out the connections between them. From that one can investigate how they get distributed, and this how they get distributed is encoded in certain coefficients called subduction or reduction coefficients. All right. So what one does is actually, once you have the infinite volume continuum operators, you can evaluate the equivalent, sorry, okay, fine. So these S here are basically referred to as subduction. Subduction is actually a bit heavy word. What you can actually instead use is reduction coefficient. Why I call this as reduction is because you are actually reducing from an O3 symmetry to an OH symmetry when you go from infinite volume continuum to the cubic symmetry. So you have limited number of operations, and your states, infinite number of states, that infinite number of irreducible representation that you had basically get redistributed into the irreps of OH, and how they get redistributed is encoded in the coefficients called as reduction coefficients. These are already evaluated out, these are already available. One can also do it ourselves, there is nothing harm. You learn something more when you do it yourself. And this way you can evaluate or construct operators that are actually good with respect to irreducible representation of the finite lattice. Here I just discussed only such construction for zero momentum. In zero momentum you have an octahedral symmetry in the finite volume. But if you consider a non-zero momentum on the lattice, then you have a non-zero momentum on the lap frame, right? Then you don't have OH symmetry, you have even a reduced symmetry, which is typically referred to as dig 2 or dig 3, etc., depending on what is the momentum that you put in. You can follow the same procedure and construct such operators, such tower of operators, and follow the same procedure that I have discussed to get the excited states. These are all I wanted to discuss at the moment, but I will just stop with a remark. I said actually we can construct all of these things following this procedure that I said, all of the excited states up to some energies based on the procedure that I have discussed. But I also discussed certain technical details in the sense that you cannot evaluate all these discontinuous diagrams with standard procedures. With a limited lifetime, we cannot evaluate entirety of it. You have to find out some other alternatives. Some alternatives or some procedures with which you can evaluate it, and that will basically be part of my next lecture. So I will again motivate about this thing again in my next lecture, so that you get a feel of why this is difficult. But assuming that this is all possible, you can evaluate the excited states in this format, and this is a standard practice these days. Thanks. Yeah.
So thanks, Padmanath, for your first lecture and questions.
I want to ask this technique of correlation matrix to find the excited states.
Yes.
I want to ask how, what is the current status of it? How good are we calculating the excited states?
So this is, no, can you please put the, yeah. So this is actually a set of excited states that we have estimated in 2017. Okay. We can do even better than this if we just use only some kind of operators. But there are issues with this kind of estimations, which I will actually say towards the end of the lecture. But you can in principle extract as many a number of states as possible. So we extract up to some 30-40 states very comfortably.
I see.
Yeah.
Any further questions? I just had a nice question. This capital DI is the with the gauge fields you are putting it, no? It's the derivative here. This capital
yes.
D.
These are covariant derivatives. Covariant derivatives, yes.